This week, Brown and Michigan froze a crystal that should vanish because they stopped treating atoms like balls and built bigger pieces. The pieces had 14 sides, like tiny Lego bricks for matter, and their soft molecular coats gave each piece room to shift. So the experiment was not forcing a crystal into place, it was asking the pieces which crystal they wanted to become. Normally, metal atoms pick one of two packed arrangements. One is tight like stacked oranges, the other leaves more breathing space. For decades, theory said a hidden middle path should exist, but the middle kept collapsing before anyone could hold it. Then the 14-sided pieces held that middle long enough to measure, and once they measured it, the room temperature surprise arrived. Electrons and light moved together without the deep freeze scientists expected. So the cascade begins here, with quantum behavior resting on a lab bench, and 4 days ago, Brown and Michigan showed the first cascade step because each 14-sided brick sits between a cube and a sphere, so it refuses both metal habits that atoms usually fall into. One habit packs outer sides tight, while the other leaves a center space, but this shape gives the stack a third route through the middle, where sticky molecular coats let neighboring blocks shift without separating. That matters because the predicted bridge phase normally disappears too fast, so the team made many shapes and watched which stacks survived, while Michigan simulations checked whether the pattern matched the exact bridge that theory had predicted. Here is the turn. The match did not just explain metal packing, it froze a missing transition into a material you can actually handle, and when light hit it, the silver electrons moved together, meaning the crystal locked light and matter together at room temperature. So the second cascade grows larger as structure becomes a quantum recipe, but this week, the twist is no longer the silver shape, because the new lattice makes light and electrons move together, and normally that lockstep asks for a freezer room world, where one measurement can depend on an entire cold machine. So room temperature does not just make the experiment easier, it changes who can even build the next test. A small lab can ask questions that once needed a fortress, and that is where this stops being a lab trick. Because when the freezer disappears, the waiting line gets shorter, and the bench worker stops borrowing someone else's cold machine. You can see the cost in the older setup. One student watches the clock while another lab owns the cold. This structure pulls that gate open a little wider, so the next quantum material may start on an ordinary bench. And the twist is not Silver learning a new trick, it is that Brown and Michigan made Silver hold the missing shape, because each particle behaves less like dust and more like a brick, and bricks can be stacked into patterns atoms usually escape. That is the payoff. A predicted middle crystal becomes touchable matter, which means the decades-old prediction finally has a sample tray. But the stranger part is what happens when light enters it, because the electrons do not just respond to the beam, they lock with it, meaning the material and light move as one. And here is why that matters to you. No deep freeze. A room temperature effect turns quantum hardware from fragile ritual into recipe. So when you see those tiny silver bricks again, you are not looking at a particle anymore. You are looking at the first draft of a warmer quantum world.